Welcome back to our routing protocol discussion, and today I'm going to be talking about Ospf. So Ospf is basically implementation of a link state protocol, or link state algorithm inside the protocol. And as a protocol, the objective is basically to discover the topology, because as soon as you get the topology, you can simply calculate the routing table, and that would be it for the protocol. So the only problem here is how to discover. And what you need to do, kind of one of the objectives is to discover and basically advertise yourself. And as soon as you receive the advertisement from everybody else, so kind of basically each router in the system will say, oh, I'm here, this is my identifier, and I have these 3 links. The other router will say basically the same thing. The other router will say basically the same thing. And eventually, if you collect enough information from everybody in the network, you, as a router, can now run the Dijkstra algorithm and calculate the routing table to all destinations in this network. And that's basically it for the protocol. On this slide, I have included Wireshark capture for Ospf protocol and a few highlights here. So first of all, Ospf is a kind of interesting protocol in terms that it's not using any UDP or TCP transport. It is directly implemented on top of UDP. And if you remember, we had one of the protocols that we discussed in this module that had the same position. Another part that will be different, or that is different, and I will highlight in a few seconds, is the fact that it has multiple headers. So in this case, I'm actually seeing only one message or one packet from each of the neighbors. And just to give you the highlight, this message contains some form of Ospf header, like generic header, following with the hello packet, basically to advertise that, oh, I'm alive. So if you receive this packet, this is the kind of me here, plus this LLS data block. I'm going to be talking a little bit more detail, not in too detail, but effectively this one is saying I'm attached to these specific neighbors. And this is kind of basically to define the topology of the network from the perspective of individual node. Compared to RIP protocol, Ospf is much more complex. At the very least, it includes at least 1, 2, 3, 4, 5 different types of headers, and I don't think I have actually included all of them. So this is just a few highlights of what kind of headers can be used. Sometimes they have some of the similarities, but just remember there are many more headers for specific functions. Because in the Ospf, you need to advertise yourself, you need to advertise what prefixes that you can reach, and these are completely separate messages, and some other information. What's important to remember? Important to remember is the fact that all the updates that you're sending about your topology, about what you're advertising, are done in terms of so-called link state packets, or LSPs. And all those LSPs have very important property. They have a sequence number and they have a kind of identifier of you. And there's some additional information like a time to live, but that's a separate story. So the important part is the identification of you as a router ID and identification of LSP message. And the reason I'm highlighting this part is because it's important for the purpose of calculating of the routing tables. In order to calculate the topology, you need to obtain the latest LSP from each of the neighbor, or like each of the router in the network. And you can actually don't care about LSPs that are older, because those represent some old state that not really current state. So that's kind of where the purpose of the sequence number in. You receive a bunch of messages, but you only care about the latest one. So you can simply ignore the old ones and don't do anything with them. Conceptually, Ospf works in the same way as RIP protocol is kind of discovers who is present in your vicinity and advertising yourself. As soon as you detect some problem, you do recalculations, and kind of in the future you announce yourself as well. The differences are how exactly and with what periodicity we actually send in the hello message, and how we notify others when we detect a problem. And this is one crucial difference. So first of all, the hello message. So the hello message is actually a very simple message. It's not really saying anything except that you're alive, your identifier, and maybe some additional information. What is different, like what is critically different, is how you notify others. So you don't notify others every 30 seconds. You only notify others if you detect the problem. So if you detect the problem, then you trigger the update. Then you create a new LSPs with a new sequence number and you send it out to others. And to improve reliability, because we're still kind of working on top of unreliable protocol, we actually send in this update, same LSP, multiple times. But kind of you can assume it's just done once. Because of the protocol is still not working on top of reliable channels, we still do some form of a so-called soft state. So we still assume there's a possibility that the other nodes in the system didn't receive our update, so we need to do something periodic, even if we didn't detect any failures, like from our perspective. But this update, compared to what we saw in the RIP protocol, is much, much, much slower. So this one is done every 30 minutes compared to 30 seconds that we were sending hello updates in the RIP protocol. The other big difference is how updates are being disseminated in the network. So again, I'm trying to compare to the RIP protocol. In the RIP protocol, there's no concept of propagating the updates, because the only conversation you have is between your neighbors. So you advertise to your neighbors and you receive information from your neighbors. So that's kind of the basic communication. What happens in the Ospf protocol is you want the update that you generated be propagated to everybody. So that's the objective. So you want to so-called flood your update, the LSP that you have generated, to every single router in a system, to make sure that you don't actually send too much, or like the updates had not been looped in a system. Ospf uses so-called reliable flooding, and basically kind of using the sequence numbers and using the state that router already have internally, it can filter out and stop propagating information about the updates it already received. So for example, if X generated update or received the update from somebody else, it will rebroadcast this update to node A and C, following that ASC will also rebroadcast this information, except to the interface that they received this update. And finally, B will try to advertise this update further, depending on how the update was received. For example, if the first update came to B, so then B will try to advertise to D and A. And at the point of the update was received at A, the A will simply know that it already received LSPs with, from that router, from that original router with that specific sequence number, and simply ignore it. If it happened to be received update first from B, then it will do update to D, to C, and kind of in that case, it will be C's responsibility to ignore that update because it's already received. But just remember, exactly the same update being propagated throughout the network, compared to RIP, that basically only propagation. It will eventually happen in RIP, but it just will happen in completely different form. And as a small side question here, can you calculate how many LSPs which traverse every single link within an hour? And you have to answer this question, you actually have to remember how many LSPs are generated and in the whole system by each individual router, and how many LSPs will traverse each individual link in the system. This was a highlight of Ospf protocol. I didn't go into much of the details. You just need to remember that Ospf implements link state protocol. As part of the link state protocol, you need to discover the whole topology, plus you need to advertise your knowledge of the topology. Actually, it's your knowledge of the neighbors. You don't actually tell anybody else what you know kind of beyond yourself. So that's kind of one of the limitations potentially of Ospf protocol. And as a protocol side, we still have concept of soft state, so we're still assuming something bad can happen in the network. Ospf is not working on top of TCP/UDP protocols, it's directly working on top of IP protocol. It has some limitations because of that. For example, you cannot really run two Ospf daemons, because then they will be conflicting to each other, because we effectively lost the demultiplexing function. And another part of the protocol is that the updates are created, I already mentioned the updates can be created periodically every 30 seconds if nothing happened. But if something happened, if I discover that, there's new information available, or new neighbor available, new neighbor appears, then I immediately send out this information throughout the network. So in this respect, Ospf is actually quite better, because as soon as it detects a problem or detects a new connectivity, and it will try to inform the whole network about that connectivity. And as a small side note here, in Ospf, you require to notify everybody in the system. Versus in RIP protocol, we only notified our immediate neighbors, and from that, through iterative process, everybody got informed if needed about something, some changes. So, like as a highlight about why is it problematic. So, for example, if you have a new connectivity, like some update of the weight of your neighbor, in Ospf, you will have to generate the basically new update. You have to propagate this update throughout the network, and everybody will have to rerun the routing protocol. And if no next hop actually changed as a result of this weight change, then it's basically the waste of resources. In RIP protocol, this propagation will basically be stopped at the neighbors. But in Ospf, this update got propagated throughout the network. But don't take me wrong, Ospf does not actually imply that it has more messages exchanged in the network. And I didn't ask the question about the RIP about the previous slide, but it really depends on a specific use case. And finally, that I did not mention explicitly, but this is the part of Ospf protocol, are the weights. So Ospf is no longer required to have only kind of up to 15 as a metric of the links, and actually in RIP, the cost of individual link is 1, and this is basically a hop count. In Ospf, the weight can be anything, and this is actually defined by the system administrator what the weight is, and then it is getting as input to Dijkstra algorithm, which calculates the shortest path in terms of the cost of the individual links. Okay, so that was yet another intensive part of routing protocols. I hope it was interesting, and see you in next module.